As we described in the previous lecture, the strategy here is to knock off things that we're already pretty much familiar with. And so we're going to jump down to the vertical um, mirror plane operation, sigma v, and that produces the analogs of the 2D ones we've already done, which is 2mm, 3m, 4mm, and 6mm. So we see this here, and it's really a complete analogy to what we've already done. Again, if we were looking down on this, we would see that, we've inserted an a pi axis, and we run this vertical plane through it. And it turns out that we have the same combination theorem we had before. Recall that we had the a sub mu, where mu is any angle, and that if we put a mirror plane on it, that we end up with another mirror plane, which is this divided by 2 away, right? So here, it's no different, just like with the 2mm. If I take a twofold axis and I put a sigma v vertical plane through it, it induces one that is pi over 2 away because the rotation's pi, so pi divided by 2, and that gives me this other plane. So looking down, it's completely analogous, and here we've just shown you that it's like these two planes intersecting with a strip down the middle. Now, to show you how this would look in our stereographic projections. So if we put a mirror plane down the middle here, right, then what happens is, if I have my classic case here of first taking this guy, now remember I have also in this diagram over here, I've got a twofold axis that's in the middle, right? And so what that does is the twofold first gives me on the same side of my sphere the same object over here. However, the mirror plane reflects this across here, and so the same side, I have the object here. So again, in our notation, now I would have a mirror plane in this, the one that shows the symmetry elements. I have a mirror plane that cuts through there. And so I have my little representation because I've got the symmetry elements over here. And then I have the motif that's induced by adding this vertical plane. Now what I don't do is I don't show necessarily, I don't have to show that there's another mirror plane here, but there is over here, you can see, right? And you can tell that there's one here because the motif gets reflected this way as well. So this is going to be true for all the n MMs. This is the identical derivation to what we did before. And remember, just like in the 3mm, the 3m doesn't produce any new mirror planes because the plane has to pass through. So in the case of 3m, I'm going to have that. And let me, let's say, put a, from the rotation point of view, sorry, let me go back. From the rotation point of view, I'd say, I have these 120-degree things here, right? But if I now add a mirror plane, when I add a mirror plane here, it just doesn't stop here. Remember, it just passes through the whole thing. So what that does is it actually induces, this line to come over on the other side. And remember, when we looked at our theorem, it says that I'm going to have a mirror plane this far away, but I already have one there because, you see, because I have to carry this through to the other side from the threefold symmetry. The truth is that this theorem, which says, I have a 120, so 120 over 2 is 60, but remember this is already 60, and I got it just from having a mirror plane pass through a threefold axis, which is why it's only called 3m instead of having the extra m. That's different from here, where I pass this through a twofold axis, and in principle, if I didn't have this guy, that's fine, because if I flip this around 180 degrees, it sits on itself. So that would be 2m. The problem is that we know from our theorem that, and you can see with the motifs, it always produces another plane there, and that's why it's called 2mm. So just reviewing that, we already talked about that in the 2D, but it's the same in the 3D. So just to summarize what I have to, without having to do each individual one, I can come down here and show you those. There's the 2mm that we just did. And here's the 3m that I just showed you. And you can see here what's occurred, right? Is that I have these the mirror planes that create these motifs, and then over here they're trying to show you that there's additional reflection around these guys, right? And so that's a 3m, 4mm, same thing, right? We already did this in the 2D case, right? And remember, we get these 45-degree mirror planes. And then, of course, the 6mm. And so now, we've kind of covered all these guys across the top, those top 11. And now we can cross off these guys right through here. So next, what we're going to do then is finally go to our horizontal plane, which is kind of unique now. Can only do that in 3D. And that'll produce some new groups. And notice how the notation, international notation, that when you have a perpendicular, horizontal plane compared to the axis that you're referring to, you actually have a slash to show that the mirror plane is perpendicular to the rotation axis.